We have finally made it to the end of an asteroid-filled week full of dart this and dart that, including the actual impact of the spacecraft into Didymos's moon Dimorphos. Like any highly anticipated mission, the media hype was on point, and the mission teams were exhausted. I hope you all enjoyed my slightly giddy interview with Amanda Sycophus that we recorded the following morning. Today, while we do have one more pair of DART images to share, we also have a new exoplanetary system and a really distant globular cluster to talk about. All of this and more, like This Week in Space History, today, here on the Daily Space. Pamela is still battling her injury, so I am your host, Beth Johnson, and we are here to put science in your brain. One of the most fun ways to track down objects in our galaxy is the ancient globular clusters. They swarm in a sphere around the disk of the Milky Way, and many are older than the bulk of the stars in our galaxy. As we've been able to look at more and more galaxies, we have only found a handful of youngish globular clusters. These few systems hint at violent origins within the shock waves of merging systems. It has been hoped that as we look farther and farther back in time by looking at more and more distant systems whose light takes all that time to reach us, we'll be able to find younger clusters and perhaps even discover the time when globular cluster formation was common. Hubble tried. Hubble looked back as far as it could, directly look with the Hubble deep fields. Hubble peered and lensed systems made visible by the gravity of massive globular clusters, but all it saw was fuzzy smears. Hubble tried, but Hubble's 2.5-meter mirror was just too small to do the job. But now we have JWST with its 6.6-meter mirror and amazing new possibilities. In JWST's first deep-field image, an image of the galaxy cluster, distant lensed galaxies are seen with never-before-realized clarity. This image alone will take years to fully analyze. One of the first papers to come out of this image was led by Lamia Maula and appears in the Astronomical Journal. This 9-page analysis focuses on just one distant galaxy, magnified by the cluster's gravity, called the Sparkler. According to Chris Willott, quote, "Our study of the Sparkler highlights the tremendous power in combining the unique capabilities of JWST with the natural magnification afforded by gravitational lensing," end quote. And the cluster's gravity shows us 3 lensed versions of this one system. From these directly distorted images, researchers were able to determine the Sparkler is 9 billion light years away, and the Sparkler was already old, with no longer star-forming globular clusters just 4.5 billion years after our universe formed. According to team member Karthik G. Iyer, quote, "Looking at the first images from JWST and discovering old globular clusters around distant galaxies was an incredible moment, one that wasn't possible with previous Hubble Space Telescope imaging," end quote. And it was a moment in which we gained no insight into how globular clusters form. Like Athena emerging fully adult from Zeus's head, globular clusters just keep emerging fully formed in our images. I, for one, am hoping that future research on other lensed systems will reveal even more ancient galaxies and just once let us clearly see how globular clusters form. Okay, new topic. While globular cluster origins remain elusive, planets are making themselves seen. It's been a few weeks since we had a good exoplanet discovery announcement, and the last one involved baby exoplanets. This week, in a new paper published in Astronomy and Astrophysics with lead author Susanna Barros, a team using the ESPRESSO spectrograph at the Very Large Telescope has announced the discovery of a 5-planet system around star HD 23472. What's really exciting about this particular discovery is that 2 of those newly found exoplanets are what we call super-mercuries. To date, we have only found 8 of this type of planet, including these latest 2. And as Barros explains, quote, the team set out to study the transition between having or not having an atmosphere, which could be related to the evaporation of the atmosphere due to the irradiation of the star, end quote. Mercury is a strange little planet in our solar system. The core of our innermost world is relatively large, and the mantle is relatively small compared to other planets orbiting our sun. And we don't understand the reason. Perhaps there was a massive impact that removed bits of the planet, or perhaps that nearness to the sun evaporated some of the mantle. Now we're finding similar-ish worlds in other systems, and Barros notes, quote, for the first time we have discovered a system with 2 super-mercuries. This allows us to obtain clues about how these planets were formed, which appears to be connected to the composition of the parent star. This new system can help us find out, end quote. The masses of the planets were measured with the radial velocity method, and from the measurements of HD 23472, the team found that 3 of the 5 planets have masses smaller than that of Earth, making these some of the lightest exoplanets discovered. The 2 super-mercuries are both about 0.8 Earth radii. For comparison, Mercury's radius is about 1/3 that of Earth's. Unfortunately, further characterization of these 2 exoplanets will have to wait until the extremely large telescope is built, as the current instruments available do not have the sensitivity to gain information about the planet's compositions or possible atmospheres. Did you think we were done with DART this week? We're not. Along with yesterday's interview with Amanda Sikafous, later on in the show, I will be back with Eric Palmer to talk about his work with the mission. But first, we get to bring you new images of the IMPACT's ejecta cloud. In an astronomy first, both the Hubble Space Telescope and JWST took observations of the same object at the same time. In this case, that moonlet asteroid, Dimorphos. The 2 space telescopes captured images of Dimorphos before and after being impacted by the DART spacecraft. JWST's image, shown in red, was taken with the near-infrared camera, NIRCam, and shows a compact core as well as plumes of ejecta surrounding that center. Hubble's image, shown in blue, was taken in visible light about 15 minutes after the impact. The ejecta is stretching out from Dimorphos, with a large spike coming out from where the spacecraft actually hit the surface. JWST took 10 images over 5 hours and will capture spectroscopic data in the coming months. Hubble captured 45 images total and will monitor Dimorphos 10 more times in the next 3 weeks, focusing on the ejecta cloud and how it changes over time. We'll keep you up to date as more images and data are released. And for those listening to the podcast, you can see the images in our show notes at dailyspace.org. Coming up next, Eric Mattis brings us This Week in Space History. And after that, we'll get to my pre-recorded interview with Eric Palmer. Stay tuned.
Before there were the several generations of Canadarm and Chris Hadfield, there was Alouette-1, Canada's first satellite, and the first collaboration between Canada and NASA. This Week in Rocket History has that story. Alouette-1 began as a project of the International Geophysical Year of 1957 to 58, much like the first satellites of the US and USSR. A Canadian government organization named the Defense Research Telecommunications Establishment responded to a NASA request for proposals in December 1958. This started the project. The satellite was designed to study the upper half of the ionosphere, something not possible from the surface of the Earth. To do this, it would carry an instrument similar to the type used to study the ionosphere from the surface, called a sounder. Canada would build the satellite, and NASA would launch it and allow the use of its extensive ground station network to receive data from it. The UK also contributed 2 ground stations in exchange for access to the data. All of these ground stations were critical to the success of the project because the Alouette-1 satellite lacked onboard data storage. It gathered data continuously, but only sent it back while in contact with the ground. Engineers chose this to make the most reliable satellite possible with the technology of the day. With agreements in place, work got underway to prove that the planned instruments would actually work in space. To do this, 2 antennae, similar to the ones that would be on the satellite, were launched on a sounding rocket into the ionosphere on 2 occasions in 1961. The tests were successful. Alouette-1 launched with 2 radio antennas for its experiment, one almost 46 meters in length and the other almost 23 meters, which were deployed from inside the spacecraft when it reached orbit. These were the longest antennas launched at the time. Alouette 1 was launched from Vandenberg Air Force Base Site 75-1-2, now known as Slick 2 West at Vandenberg Space Force Base, on September 29, 1962, aboard a Thor Agena rocket. It was put into a 1,000-kilometer orbit inclined 80 degrees to the equator. Alouette 1 operated for 10 years despite a decrease in its spin rate and the Starfish Prime space nuclear test several months prior to its launch, which damaged or destroyed 10 other satellites. The success of Alouette 1 led to an expanded program called the International Satellites for Ionospheric Studies, which continued with the further 5 satellites operated through 1990. Alouette 2 was launched in 1965. It was the flight spare for Alouette 1, refurbished for launch. The expanded program included France, Norway, Japan, New Zealand, Australia, Finland, and South Africa. And now for some statistics. The number of toilets in space is 8. 4 on the ISS, 1 on Soyuz MS-22, and 1 on Crew Dragon Freedom, 1 on Tianhe, and 1 on Shenzhou 14. We keep track of orbital launches by launch site, also called spaceport. Here's that breakdown. USA 56, China 37, Russia 7, New Zealand 7, Kazakhstan 6, French Guiana 3, India 3, Iran 1, and South Korea 1. From those 121 launches, a total of 1,886 spacecraft have been put into orbit, with 1,456 of them being Starlinks. Your random space fact for this week is that Alouette 1 held the record for most publications from a single spacecraft's data until the early 1970s. The record was only broken by much larger and more complicated spacecraft such as OGO-5.
It's been a DART extravaganza this week at the Daily Space, and indeed all over the planetary science community. In case you've been living under a rock or are still scarred by counting rocks on Bennu, the DART mission successfully booped, or possibly smacked, into the asteroid Dimorphos on Monday, September 26th. Joining us today is Eric Palmer, a senior scientist at the Planetary Science Institute, who has been involved in the shape modeling of the asteroid Didymos. Thank you for joining us today, Eric.
Thank you.
So tell us about your involvement in the DART mission. What does shape modeling mean? What does it entail?
So to fully understand what is going on, we need to get an accurate representation of the surface of Dimorphos. So when the impactor hits, we need to know where it hits. We need to know what the slopes of the surface is, so we understand the angles of impact, because that will affect how much momentum is transferred into spin versus a translational energy, meaning slow the orbit down. Mm-hmm. So all of those parameters needs to be understood. So we have to take the images and we have to extract out what the shape should be. So that's one of the primary science goals that we need is an accurate shape model. And I've been doing this for several years. I'm more in the support for them in this regard, in terms of helping them with training, helping them get the shape modeling software configured and set up for this. However, we also, from a scientific standpoint, want to get an accurate shape model for Didymos. Mm-hmm. And so while they're worried about the impact and such, because they're over at the Applied Physics Laboratory, I'm over here at PSI and I'm focusing on the shape model of the primary. And that helps us understand the orbital dynamics, the evolution of the system, the stability of the system, the gravity field that it's interacting with. Of course, the ejecta as it leaves is going to be influenced by the gravity more of the primary than the secondary. So having an accurate shape model is essential. And so that's my primary role right now, is to take the images that we have and convert that into a 3D digital train model.
So walk us through what you were doing on Monday as this was all going down. I was live streaming. I was talking to a variety of scientists. Everybody was excited and on the edge of their seat. What was your day like? How did it go for you?
Um, so the morning we started off with our science meeting that, started about 7 hours prior. And so we had about a 2-hour science meeting. We talked about all the stuff. We reviewed the spacecraft status, what was expected. We had discussions about what we could and could not release to the media. We talked about a lot of the ground-based observing plans. We got a few of the images, still 7 hours out of the system, and I think they were saying that, hey, we can actually start to make out dimorphos. So that was during the science meeting, and so that excitement was really nice. It was very palatable that we were included in that. And then we go off to our respective worlds as we wait for the stuff to kick off. And yeah, probably about an hour prior, I was watching the live stream and kind of catching up. And then the background, I'm over there, and we now start getting data where the objects are spatially resolved. So that means I can actually pull them into my software, and I can take this tiny little 3-pixel or 5-pixel thing and start trying to align it with the our starting shape model. So we start we start with a shape model, we align the images to that model, and then we start processing it. So during the whole impact, I'm over on the side downloading images and trying to get them registered and make sure my system is all squared away, because obviously it's only the last few minutes that had high enough resolution data for me to do my job. So all this preliminary stuff is not it doesn't really move the needle at all, because 10 minutes later those images are so much better than the ones I had before. You just don't want to use the ones before. So it was getting that all squared away.
What were your thoughts when you started to see the detail in both Didymos and Dimorphos? Were there surprising things to you? Were there, what was interesting? What caught your attention? What made you kind of go, wow?
So I was surprised at how elongated Didymos was. So the radar shape model is a little bit more rounded, and in the images, it's much more elongated. So that was one of the corrections that I've had to make, and that was really cool. And of course, we were expecting Dimorphos to be, kind of this, oval pointed at Didymos. So we were expecting that, but I don't think very many people were expecting it to be as elongated as it was. So that's really cool. I liked on Didymos around the equator, because it's spinning relatively fast. It looks like there's smoother areas there, which is kind of cool. So that makes you think that there's mass wasting. Honestly, that is what we more expected Bennu to look like. We expected to find regions that were somewhat smooth, because Eros had that. So we were kind of expecting to see that there. That actually, in my mind, was, oh my goodness, this is what Bennu was supposed to look like, so we could take a sample. And then, of course, Bennu didn't cooperate. And then the other thing, especially when I was looking at Dimorphos, was the kind of the size distribution of the class. Clearly, it's a rubble pile, but looking at that, and I didn't see as much small stuff, the fine, kind of the fine regolith grains. It seemed like a lot more. Is bouldery an actual word? Anyway, a lot more large rock shards than fine material, and that was probably the most striking thing there. I was looking at that.
So what is next for you after the post-DART mission euphoria wears off?
Well, the bulk of my work normally goes into managing the asteroid subnode of the planetary data system, where we archive all the asteroid data. So dealing with getting the data in, running a data center, archiving standards, working with missions to help them get their documents all squared away. So that's a lot of it right now. There's a few other projects that I help out in terms of building topography on the moon, some of the Saturnian and Jovian smaller satellites, doing some work there. So that's at I more help out than actually do most of the work. They're not paying me much to do it.
Thank you for telling us how you have been involved in DART, what your day was like, and also for talking about the vast majority of your work, which I know is on the PDS system. So that's fantastic. Definitely want to talk to you about that some other time and get more into that. This has been sort of an amazing, wild week. I hope you have gotten more sleep than I have. And I know Amanda Sycophus did not get a lot of sleep either. So, and I know you also had a DART meeting earlier today. So, good luck on analyzing all of this data. And I hope that it really does prove useful for you and also in the general context of planetary defense, which is what the whole purpose was. Some of these side science benefits are fantastic though. So thank you, Eric, for joining us today and for talking to us.
My pleasure. Have a good day.
All right, you too. Thank you so much. This has been The Daily Space. To all of you watching, our pre-recorded interview ran longer than we can air here on Now Media. You can catch the conversation in its entirety on our website, dailyspace.org. While you're there, check out our show notes to find more information on all our stories, including images. As always, we're here thanks to the donations of people like you. If you like our content, please consider joining our Patreon at patreon.com/CosmoQuestX.